everyone, welcome back. My name is Mr. Cobalt, and in this video we're going to be going over the process of condensation and evaporation. So let's get into this. So first we're going to talk about the process of condensation, and then we'll move into evaporation. So what happens during the process of condensation? The first thing you need to know is the kinetic molecular theory, right? Or at least one part of the kinetic molecular theory, and that is that temperature is related to the movement of the particles. So we should know a formula for that. So the formula, right, is going to be kinetic energy average is going to be equal to 1/2 times the mass of the particle times the velocity squared. So you can see here, and this is going to be average velocity squared. So the average kinetic energy is related to the mass and the speed of the particles. Now this, according to kinetic molecular theory, this is related to, I'll say proportional for now, proportional to temperature. So temperature is a measurement of the average kinetic energy of the particles, which is related to the speed of the particles. Why is this important? Because then we can relate this to the strength of intermolecular forces, right? So that's also part of the process, or part of condensation or vaporization, is the strength of the interactions, the attractive interactions between the particles. So there is a kind of a tug of war between the speed of the particles that the particles are moving at and the intermolecular forces that are attracting the particles. Okay, so that's what we have to kind of keep in the back of our mind when we're thinking about these processes. Okay, so let's look at my picture on the board. So you'll see that these are zoomed in particle diagrams, if you will, of particles moving as the temperature increases. So let's assume that these are the particles, the gas particles moving around in our beaker, right? Or Erlenmeyer flask, right? So we have an Erlenmeyer flask and it's got water vapor. Let's assume that these are water molecules, right? So each circle represents a water molecule and they're bouncing around, and it's relatively high temperature, meaning that they are going to be moving at a relatively high average speed. Now, average means that these are an average of the particle's motion, right? So every particle is not moving at exactly the same speed, right? That would be really interesting if that was the case. But each particle is moving at different speeds, so we take the average. So the temperature is the average speed. So at relatively, I should change this to decreasing because we're talking about condensation. I'll change that later when we talk about evaporation. So this should be cooling or decreasing temperature. So we're going to decrease the temperature. Okay, so we're going to start at relatively high temperature here. So the particles are moving relatively fast. So what's going on at the particle level? So here, because they're moving so fast, right, you got to remember that these attractive particles, at the very least, they have London dispersion forces, but also if we're talking about water molecules, they're going to have hydrogen bonding, right? So hydrogen bonding is relatively strong, right? But as these particles are moving around, they're going to collide into each other, right? So when they collide into each other, right, you're going to feel, right, you might feel an attractive force, but if the speed is so fast, if the momentum is so high, right, they're going to collide into each other, but then they're going to ricochet off of each other. They're not going to stay in contact very long because of the high speed, right, the relatively high speed. So when they collide into each other, the collision is so fast and so strong that the intermolecular forces don't really have a chance to interact, to stick them together, to what's the one I'm looking for? They don't have time to attract long enough for the particles to stay together. So they're going to be elastic collisions, right? So elastic means that energy is not lost, they're not going to stick together, right? So they're going to bounce off of each other. So they're moving so fast at this temperature that they don't really have the time or the ability to attract each other as much, right? Because of the strength of the collisions, the speed of the particles. Okay, so if we decrease the temperature a little bit more, what do we notice happening here? So at a lower temperature, they start to slow down. The average kinetic energy goes down. The speed of the particles goes down. And here's where you might get some sticking together, right? So here they're still moving relatively fast, but this time when they collide, some of these particles, if they are moving slow enough, can then be attracted to each other, and instead of ricocheting, the ricochet will not be as strong, and it won't be as strong enough to have the particles just separate from each other and ricochet. So here you have two particles that are stuck together. Now they're moving together as one, right? Here we have three particles stuck together and they're moving as one. So at a lower temperature, the collisions aren't as strong. Not all the collisions. Remember, this is still an average, right? So some of these particles are still moving too fast and they collide too strongly in order to stick together, right? But some of them, right, as an average, some of them are moving slow enough that when they do collide, the intermolecular forces are going to be strong enough to attract them and stick them together. So you'll get two, maybe three particles stick together and then they move as one. So here's at a lower temperature. So you start to see this clumping together, right? So they're going to clump together, they're going to move more slowly, and then as you lower the temperature even more, the clumps get larger. So these three might bump into those two and make a clump of five, right? These two might be collide and they might make a duet, right? So as you lower the temperature, you still have these collisions, but the collisions are not going to be strong enough to break them apart, right? So here, right, you have these two together, but what might happen is another one of these fast moving particles might hit those and break them apart, right? That's a possibility at this stage, right? But when you lower the temperature enough, then everything kind of slows down enough where the particles start to really clump together, and now you get this larger clump. So you might get larger clumps. These smaller clumps bond together, as I said, to get larger clumps of five. The five might bump into another five, and then you get 10, and so on. And so you build up these larger clumps of particles, in this case, water molecules. And what happens? You start to form drops. You start to form little drops and then bigger drops. And then you get liquid water here. This is the liquid water that starts to settle down into the Erlenmeyer flask as it builds up on the sides, right? You see the water droplets on the side of your Erlenmeyer flask, and if those drops get large enough, then it'll trickle down the side and get to the bottom of your flask. Right? And so now you have liquid water. And so now you have a bunch of particles that are relatively close together. They're kind of stuck together, really in close vicinity of each other. But they can still move around, right? They're still moving around, but they're relatively close. They're still bumping into each other more frequently because they're kind of more packed together. But they can move around still, right? So here you've got water. So this would be liquid water here. This is where you're kind of getting the clumps to start to form, right? And so the idea here is as you are decreasing the temperature, you're slowing down the particles. They have less energy, less kinetic energy, meaning that the attractive forces are going to be relatively stronger. Now, the attractive forces are not changing, but the speed is. But you're giving the attractive forces time to pull them together, pull the particles together and form clumps, right? So as the temperature decreases, you're slowing down the particles. The particles are colliding with each other here, but the collisions are too strong to allow the interactions to do their work, right? To stick them together. As they slow down, now the intermolecular forces are able to attract and stick particles together. And as you lower the temperature, you're going to decrease the speed, and more particles are going to be able to be attracted together by the intermolecular forces, and then you end up getting a liquid, right? So that is the process of condensation. Well, what about the process of evaporation? Let's talk about that next. Okay, let's talk about evaporation now. So here we're asking the question, well, how does evaporation occur? What is the process of evaporation? How do those particles become gas again, or vapor? So here I have a couple of pictures again. Now we're in the liquid phase, and we're gonna see how does a particle become a gas again. Well, as we saw before, the particles are relatively close together. They're moving around, they're jostling around here. And so they're relatively close together in the liquid phase. Now here, I want you to imagine that this is a close-up of the particles that are in a closed container, right? So we talked about our Erlenmeyer flask. Let's say there's a stopper on the Erlenmeyer flask, so it's a closed container. The gas particles can't escape. So they're going to stay in the Erlenmeyer flask, and maybe at the bottom of the Erlenmeyer flask you have a liquid, say water again. So here, close-up look of particles of water, the water molecules, and so they're very close together. About 70% of a liquid is going to be filled with particles, right? The rest is space. So there is space to move around, but not a whole lot of space, right? So imagine yourself, you're walking in a very crowded room and you've got to bump into people, you got to squeeze past people and move around, right? So as you're moving around the room, you are hitting and bumping up against people and squeezing by people. So that's kind of the analogy of what's happening to the particles in a liquid. So they're relatively close together. And again, as you're jostling around, as you're moving around, you are able to move from one side of the container to the other. You can go move to the bottom, you can move to the top near the surface. But the whole time you have intermolecular forces acting on you as a particle, right? So here, right, this particle here is interacting with the particles around it, so they are attracting each other. So as you're moving around the room, or as you're floating or jostling around the liquid in the Erlenmeyer flask, you are forming attractions between particles, and then you break those attractions, and then you form new attractions with other particles. So the whole time you are undergoing attractive forces from other particles. Now, as you're moving along, right, you can reach the surface. So at the surface, it's a little bit different, right? So here, when you're inside the liquid in the inner part here, you're surrounded by other particles, right? So you're being attracted, you're forming attractions with other particles all around you. But at the surface, you'll notice that there are no attractive forces up here. There's no particles up here. This is just open space at the surface of the liquid in your Erlenmeyer flask. So here you only have attractive forces below. So if you are moving fast enough, and remember, just to remind ourselves that temperature is a measure of the average kinetic energy of a substance, right? And that's equal to the 1/2 times the mass of the particle times the velocity squared, the average velocity squared. So we're talking about an average kinetic energy. So some particles are moving slower, some particles are moving faster. So up here, you're only being attracted by certain particles at the surface below, right? So if we look at this particle here, we see that these three particles are attracting it, right? But if this particle has enough velocity, then it can move beyond the surface, right? Now, if it's not moving fast enough, it might move a little bit beyond the surface, but then the attractive forces will pull it back, right? But if this particle here has enough momentum, enough velocity, enough kinetic energy, it can break free from the particles. Also, these three particles, they could be moving in the same direction. They could actually simultaneously bump into this one, or close to simultaneously bump into this one and give it a good kick, and it'll get that momentum and get that kinetic energy that's absorbed and move out of the surface, right? So if it moves far enough beyond the surface, then it can break those attractions. The attractive forces won't be strong enough to pull it back in. And then what you got here is your free particle, your free water molecule. So now your water molecule has become a vapor. It's part of the vapor phase or gas phase, okay? You use the word vapor for particles that are in the gas phase, but at normal temperature, they're typically a liquid, right? So if we're at, room temperature for water, then if a particle of water, a molecule of water breaks off, then we would say it's in the vapor phase, right? Because typically at normal temperatures, it's going to be a liquid, but it's a gas. So now we have it in the vapor phase here. So now this particle is free to move around, and it's got enough energy to do that. Now, oops. Sorry about that. So that is how particles escape from the liquid, right? So they have to be at the surface, right? And they have to have enough momentum in order to escape. And so there's a few criteria that the particles need to meet in order to escape from the surface, from the water phase. One, of course, it's got to be at the liquid surface. If it's not at the liquid surface, it's not going to evaporate. It's not going to break free and join the vapor phase. So particles here are surrounded by other particles, and therefore they're surrounded by attractive forces, and they're not going to escape. So you've got to be at the liquid surface. Number two, its direction and motion must take it beyond the liquid surface. So it's got to reach beyond the liquid surface. So again, if it doesn't have enough momentum, and if it's not going in the right direction, it's not going to break free of the attractive forces of other particles, and it's not going to be able to move beyond the surface. So it's got to move in a direction, and motion must be beyond the liquid surface. And then three, its momentum must be great enough to overcome the backward pull of the other particles at the surface, right? So it's got to be at the surface. Its direction of motion, it's got to be pulling it. It's got to be going beyond the surface. It's got to be going this way. It can't be going this way, right? This one is at the surface, but it's going in the wrong direction, right? So that's not going to help. So it's got to be at the surface. Its motion and direction has to be moving beyond the surface, and its momentum must be, and its kinetic energy must be great enough to overcome the attractive forces that are trying to pull it back, right? If all three conditions are met, then you will have a particle that is going to be released into the vapor phase and become gas. Okay, so this actually will explain why evaporation cools down the water or cools down the surface, right? So why is that? Why does water cool down when you have evaporation? Or why does the liquid cool down when it evaporates or as it's evaporating? Well, if you remember, again, going back to temperature is a measure of the average kinetic energy of the particles in a substance? Well, if the particles are moving fast enough, right? And again, remember, speed is related to average kinetic energy, right? So the faster particles, the ones that have enough kinetic energy at the surface to overcome those attractive forces and then become vapor, well, the liquid that's left over is losing those faster particles, right? So if the liquid is losing faster particles and the speed of the particles related to kinetic energy, which is the measure of temperature, that's what temperature is measuring, then over time as the liquid evaporates, more and more of the fast particles are going to be removed from the liquid, and therefore the average speed of the particles left over is going to be less, which means that the average kinetic energy is going to be less, and that means the temperature is going to be less. So that's going to cause a cooling of the liquid. Okay, so that is evaporation. Now we're going to talk about the rate of evaporation and what affects the rate of evaporation. So stay tuned. Okay, let's talk about the rate of evaporation now. So when it comes to the rate of evaporation, there are three factors involved. So the rate of evaporation depends on three factors. The first factor is the surface area of the liquid. The second is the strength of the attractions between the particles in the liquid and the temperature of the liquid itself. So let's talk about each of those in turn. So for the surface of the liquid, as we talked about just a moment ago, the only particles that are able to evaporate or go into the vapor phase are the ones at the surface, right? So remember, the ones that are within the liquid below the surface, they're surrounded by particles, therefore they're surrounded by attractive forces, so they're really not going to escape from the liquid phase. So you need to be at the surface where you only have the particles beneath or on the side that are attracting, so above you don't have any attractive forces. So you need to be at the surface. That was one of the criteria in order to go from the liquid phase to the vapor phase. So it makes sense that if you increase the surface area, therefore you would increase the rate of evaporation. And here's the idea, right? So you increase the greater surface area, or you make the surface area greater. That's going to increase the number of particles that are at the surface of your liquid, right? So remember, we're keeping the temperature the same, right? We're not changing temperature, so the temperatures are the same. But if you just increase the surface area, you are now going to increase the number of particles that are at the surface. Therefore, the number of particles that are at the surface is going to increase, and the particles that have enough energy to escape is going to increase, right? So increasing that, more particles with enough energy, enough kinetic energy to escape from the surface will be at the surface, right? And so therefore you're going to have a higher rate of evaporation. So here I have kind of an example, right? So here I have a test tube with water in it. You could see that you got a bit of water in there, but notice the surface area is really small. So only the water particles or water molecules at the surface are going to be able to escape. All of this water, the particles, the water molecules are trapped, right? Now they can move around and go to the surface, but there's only a certain amount of room at the surface, right? So if another water molecule goes to the surface, then that's going to push another water molecule down, right? Another water particle down. Okay, so now here I have a beaker, very large beaker. If I pour the water into the beaker, now look at that surface area. So there's just enough water to cover the bottom of the surface, and now you have all of that surface area. So now you've increased the number of water molecules at the surface. And so now you have a lot more water molecules that are able to escape, that have enough energy to escape, right? So I would expect if I had the same amount of water in here versus in here, I would expect that the water in this large beaker is going to evaporate more quickly than the water in the test tube, right? And you could try that at home if you want. Now, one of the things you could do at home, now again, do this with your parents' permission if you need permission, is you could take a little bit of water in a small container like a test tube or something like that. And then you could take some of it and just put it on the table, right? Spread it on the table and then wait to see how fast it'll evaporate. If you spread it enough, you'll see that it evaporates pretty quickly versus being in a small container. So you could try that at home and make your own observations of that. Okay, so the other thing we want to look at is the strength of attractions between the particles in the liquid. So if you have experienced, say, acetone or nail polish remover, which is basically an acetone solution, right? So if you've used nail polish remover or acetone, you've noticed that it evaporates pretty quickly compared to water, right? And that's because that acetone particles, the acetone molecules, have a weaker attractive force compared to water. Acetone does not have hydrogen bonding, right? But water has hydrogen bonding. So water has stronger attractive forces, so it's not going to evaporate as quickly, right? So weaker attractive forces means that you can escape more easily with less amount of energy, right? So if we look here, right? So if you have weaker attractions between the particles, right, like acetone, then that'll lead to a lower momentum being needed to escape from the surface area, right? So if you have particles, again, we're at the same temperature, temperature is constant, we're not changing temperature, it's just we're looking at the attractive forces. So if you have weaker attractive forces like in acetone, like, right, acetone has weaker attractive forces, it says dipole-dipole attractive forces versus hydrogen bonding in water, right? That means that the threshold energy that you need to break free of those attractive forces is going to be less, right? So you don't need to have as high of a momentum or as large of a kinetic energy in order to break free from those weaker attractive forces, right? So the barrier is lower, right? So you can escape from the surface more easily. Therefore, at a constant temperature, a greater percentage of the particles at the surface have the needed momentum, right? So lower threshold, more particles, a greater percentage of particles have the needed momentum and needed needed kinetic energy in order to break free of those attractive forces and escape, and therefore you're going to have a higher rate of evaporation. Okay, and again, you could do this at home, and again, with your parents' permission if you need it. If you have some nail polish remover in some water, you could take, measure the same amount of water, the same amount of acetone or the nail polish remover, and again, put it on a surface, maybe a table of some sort, like a glass table or a table that's not gonna, be ruined by anything. So you can put a little bit of acetone and a little bit of the water on the table, and you can observe which one's going to evaporate faster. You'll probably notice that the nail polish remover will, or the acetone will evaporate quicker. Okay, last one, the temperature of the liquid. So again, temperature is related to the average kinetic energy or the average speed of the particles. So if you raise the temperature, you're going to increase the amount of speed or the amount of kinetic energy in the liquid. So you're going to get a greater percentage of particles in the liquid that are going to have enough kinetic energy, enough momentum to break free of those attractive forces at the surface. So if you raise temperature of the liquid, right, increased temperature is going to lead to an increased velocity and momentum of the particles, right? On average, you're going to have more particles with a high enough energy, high enough speed, momentum to break free from those attractive forces at the surface. So again, you're going to increase the percentage of particles with the needed velocity and momentum to escape, and then therefore you're going to increase the rate of evaporation. And so this is the factors that involve in the rate of evaporation. Again, it's going to be the surface area, right? Increased surface area increases the rate of evaporation. The strength of the attractive forces, the weaker the attractive force, the more easily the particles can break free from the surface, and therefore they can evaporate or become vapor more easily and more quickly. So the rate of evaporation goes up. And again, the temperature of the liquid. If you increase the temperature, you're going to increase the speed of the particles, increase the kinetic energy, and therefore more particles are going to have the needed energy to escape and break free from the surface, those attractive forces, to escape from those attractive forces. And so that is how the rate of evaporation is affected by those three factors. Thank you for joining me. I hope you enjoyed the video. If you did, then please like, subscribe, make a comment down below. Let me know what you think about the video, and I would love to hear your thoughts. Thanks for joining me, and have a great day.